Hello, everyone. Thank you very much for joining us for this first ever QuantMinds Digital Week webinar on machine learning asset allocation. My name is Vincent and I'm the editor for RiskMinds and QuantMinds international brands. So before I hand you over to Marcos, I would like to quickly share with you how you can make the most of the webinar and importantly, how to submit questions to us. So if you hover over your toolbar, you will see an icon that looks like a speech bubble. When you click on that, you will see the options to submit your questions on the side of your screen. I would encourage you all to submit your questions throughout the webinar, and we'll address as many of them as possible towards the end of the presentation. And if you know of people who couldn't make this live presentation, the webinar will be available on demand this Friday in our upcoming e-magazine. So not to hold you any longer, now I'd like to welcome Marcos Lopez de Prado, CIO of True Positive Technologies. Marcos, the floor is yours.
Thank you, Vincent. It's a pleasure to be here today and introduce some techniques that I think will be very useful for practical applications in finance. As you know, over the past 50, 60 years, the paradigm for portfolio construction has been Markowitz style solutions, efficient frontier, convex optimization, etc. And this approach has a number of caveats that machine learning can help address. Typically, when we think of machine learning, we think of price prediction, but in fact, I'm quite confident that one of the strongest applications of machine learning in finance is portfolio construction, risk management, execution, and other applications that people typically do not pay so much attention to. And let me motivate why that's the case. When you think of portfolio construction, there are two sources of instability, two sources of problems, two reasons why convex optimization methods like Markowitz, Black-Liderman, and other refinements fail. And the two reasons are, number one, noise that comes from input variables, and number two, instability associated with the signal structure of the input variables. And machine learning can help us address these two sources of instability in a very effective way. Let's see how. The problem statement is the following. We're trying to build a portfolio of n random variables, n stocks or and bonds and futures. And what we have is two inputs. Number one, the array of expected excess returns, mu, and the covariance matrix of excess returns, v. Given that the traditional approach is to try and optimize a vector omega such that we minimize the risk of the portfolio, the variance of the portfolio, subject to achieving a particular goal. This goal can be achieve a particular expected return or some other characteristic portfolio, which is determined by this A array. For instance, if you replace this A array with mu, then the solution is that we are going to maximize the Sharpe ratio portfolio. If you replace this A array with entries equal to 1, then the solution is going to compute the minimum variance portfolio. One way to solve this problem in the case of equality constraints is to apply a Lagrangian, and as you can see here, we solve for first order conditions, and what we get is this traditional solution. What I want you to pay attention in this slide is not about this derivation. This derivation will change depending on whether we are solving inequality constraints or if we apply Karush-Kuntaker, for instance, for inequality constraints. What is important about this solution here at the bottom is that it requires two things. Number one, that we invert the covariance matrix, and number two, that we multiply this inverted covariance matrix with the array the characteristic array A. This is problematic. Why? Because even though the solution, as we can see here, will be truly a minimum risk subject to achieving a particular goal as we wanted, the problem is that we do not know precisely what is the true covariance matrix, and we do not know precisely what is the vector or the characteristic vector. For instance, if we are replacing it with the vector of expected returns, we just cannot forecast returns with high precision. So when we replace these two inputs in the convex optimal solution, what we get is that we are operating with very noisy inputs. Let's see what this means in practice. The first thing I'm going to discuss is noise-induced instability, and I need to define this properly. The Marchenko-Pastor distribution is the distribution of the eigenvalues of a random covariance matrix. So suppose that you have a matrix X of size T by N, where T is the number of observations and N is the number of random variables. And this matrix is a random matrix with zero mean and a variance of sigma square. Well, what the Marchenko-Pastor theorem tells us is that the eigenvalues associated with the matrix C, which is essentially the covariance matrix of X, will follow this distribution. The eigenvalues will follow this distribution, all right? And as you can see, the distribution depends on the number of observations T, the number of variables N, the sigma, meaning the variance of the observations, and also these two parameters, L plus and lambda plus and lambda minus, where lambda plus is the maximum boundary of the eigenvalues, and lambda minus is the minimum boundary. Well, the maximum boundary can be computed as sigma squared times 1 plus the square root of N divided by T, and lambda minus can be estimated as computed as sigma squared 1 minus the square root of N over T. What is important about this expression is that when we increase the number of columns relative to the number of rows, lambda plus increases and lambda minus decreases, meaning that the distribution of the eigenvalues widens as we have more variables than observations. Well, that's intuitive, right? We would expect that if we have many stocks relative to the number of observations, the eigenvalues are going to become more extreme. This is why the condition number of covariance matrices that are very high dimensional is very high. So the Marchenko-Pastor distribution systematizes and formalizes something that we knew intuitively. Let's see a particular application in finance. And here I'm going to follow an approach that appeared in 2005, written by Lelou and other authors. Essentially, what they argue is that we can fit the Marchenko-Pastor distribution to a covariance matrix derived from finance. For instance, derived from VARA. If you take the VARA covariance matrix, it's a covariance matrix that is derived from a number of factors that are estimated. So it already imposes some structure that should help reduce some of the noise included in that covariance matrix. And what they find is that once we fit the Marchenko-Pasteur distribution on these covariance, on this structural, on this factor-based covariance matrix, what we get is that a tremendous number of eigenvalues fall under the Marchenko-Pasteur distribution. Then there is a gap in the eigenvalues, and then there are some high eigenvalues that would not have been predicted by Marchenko-Pasteur. So essentially what this is telling us is that we can use Marchenko-Pasteur to separate the eigenvalues associated with noise, the ones that you would obtain from a random covariance matrix, from the eigenvalues that are so high that cannot be associated with noise. They must be associated with signal. So this is an extremely important finding. We can use Marchenko-Pasteur to separate eigenvalues associated with noise from eigenvalues associated with signal. Let's see how. There are several approaches. The first approach is, given that there are many eigenvalues associated with noise, we can just center them. Remember, they are noise. We can really, they don't contain any information. We can transform these eigenvalues in such a way that they help us improve the numerical properties of the covariance matrix without fearing that we are going to lose any information. So what we can do is we can replace all of those eigenvalues falling under the Marchenko-Pasteur distribution with their mean. By centering these eigenvalues, what we achieve is that now L minus will be higher. Essentially, the minimum eigenvalue associated with this covariance matrix is going to be higher, and therefore the condition number of the covariance matrix will dramatically reduce. This is very important because if you remember from the second slide, we said that in order to compute the optimal portfolios, we needed to estimate the inverse covariance matrix. Well, the inverse covariance matrix is, of course, a function of the determinant of the covariance matrix. And if you recall from linear algebra, the determinant of the covariance matrix, it can be estimated as the product of the eigenvalues. If you have a very small eigenvalue, what happens is that the determinant will be very close to zero, and the inverse covariance matrix will explode. This explosion of the covariance matrix translates into instability. Why? Because if you have a very small error in your forecast of returns, and you are computing these imperfect estimate of the returns with the covariance matrix that has exploded, the efficient frontier will be all over the place. You will just change one row in your X matrix, and the solution will be completely different. So this is something that researchers have known for decades. And the framework that I just explained to you illustrates why. It points exactly to the reason why Markovitch has been so unstable. And the reason is that we need to denoise the covariance matrix. So that's what we have just done when we replace the eigenvalues that fall under the Marchenko-Pasteur distribution, fitted using machine learning, using KD, right, using a kernel density estimator. We replace those eigenvalues that fall under Marchenko-Pasteur with their mean, and therefore the condition number of the covariance matrix is lower. We can inverse that covariance matrix without exploding. And that in itself will stabilize the solution. The second approach would be to shrink only the eigenvalues associated with noise. If you recall from a few slides ago, we said that Marchenko-Pasteur allows us to separate eigenvalues associated with signal from eigenvalues associated with noise. And that's great because that means that we can treat numerically only the eigenvalues that need to be treated. We can leave the signal alone and shrink the eigenvalues associated with noise. And this is what I'm showing you in this plot. For the eigenvalues associated with noise, we leave them essentially as they are, And for the eigenvalues associated with signal, we leave them essentially as they are. For the eigenvalues associated with noise, we shrink them. We apply a shrinkage estimator, for instance, Ledois-Wolf or other shrinkage methods to bring that portion or those components of the covariance matrix closer to the diagonal. This is a very important difference relative to other sections of the literature. As you know, there are many papers in the literature that propose shrinking the entire covariance matrix, and that's not a good option. Why? Because the covariance matrices that we work with in finance, they have a very low signal to noise ratio. If you shrink those covariance matrix, you are diluting the very dim signal even further. So what we need to do is we need to separate the eigenvalues associated with signal from the eigenvalues associated with noise so that we shrink only the eigenvalues associated with noise. And that's what we are doing here. Again, the difference between these two approaches is just that in the first approach, we replace the eigenvalues associated with noise with their mean, with a constant value. And in the second approach, we replace the eigenvalues associated with noise with their shrinkage estimator. It's a very small difference. And I think that you will see in practice that both approaches lead to very good improved solutions. Let me stress that in the literature, you will definitely find papers that claim that the shrinkage alone without any denoising works. Typically, the empirical evidence is presented in the form of a backtest. And as you know, backtest, to overfit a backtest is trivial. You just need to run a number of experiments and identify the proper securities, the proper time period, and the results will be whatever you want them to be. This is not what we are talking here, right? What we will evaluate the mathematical properties of this approach using Monte Carlo experiments where we have a perfect understanding of the properties of the correlation matrix, and we can control for those properties and see how the method responds. And we will see what is the benefit of using denoising compared to using a shrinkage. All right. I would also like to introduce the notion of detoning. What detoning means is that in financial covariance matrices, there are one or two very strong principal components. These principal components are typically associated either with the market component or maybe some very strong risk factor like sector or region. Unless we remove these very strong components, the tone, the information that comes from these principal components can be so dominating that the empirical methods will fail to see other more nuisance, more detailed information, more subtle information contained in the covariance matrix. So particularly when you are working in clustering problems, it is a very good idea to detone the covariance matrix. Why? Because once you remove the tone, now the clustering algorithm can see what remaining information allows for clustering. Otherwise, when you cluster a covariance matrix without detoning, everything is dominated by a single cluster, right? The market cluster. Once you remove the market cluster, now you allow the clustering algorithm to pay attention to other sources of mutual information, like sectors, industries, etc. How do we detone? Well, it's relatively simple. What we need to do is we need to apply a spectral decomposition of the correlation matrix. We identify what is the one or two principal components that are associated with the tone. We remove them from the covariance matrix, it's just a subtraction. And then, given that, we can reconstitute the Detuning covariance matrix. That means that we have removed one or two principal components from the correlation matrix. The correlation matrix is now going to be singular as a result of removing one or two components, but that's not a problem, because what we can do is we can optimize the portfolio on this reduced correlation matrix, right? Where we have, again, removed one or two components, and then that solution can be mapped back to the original space. So numerically, this is a relatively straightforward approach. But does this approach work? Well, again, there are two ways to answer this question: the wrong way and the good way. The wrong way is to now run some historical backtest that will not really reveal much, in the sense that a historical backtest is anecdotal evidence. It's important to run historical backtests, but the evidence that we will get will typically be anecdotal. Why? Because the conclusions will all be referred to a particular path that the stochastic process has followed. A historical backtest doesn't allow us to explore all the alternative realizations that could have occurred. They just show a particular realization. So that's why I say historical backtests are rather anecdotal. They don't tell us whether a mathematical method is valid or not. They don't demonstrate what are the mathematical properties associated with a particular approach. Instead, the right way to evaluate those properties is with Monte Carlo experiments. One potential Monte Carlo experiment would be the following. We generate a vector of means and covariance matrix, or we take a vector of means and covariance matrix from the market, and given that vector, whether it is synthetic or an observed one, we can perturbate it, right? We can sample observations from this distribution, and for every time that we sample an entire X matrix from that distribution, we can compute a correlation matrix and optimize. This optimal portfolio is based on a sample from a ground truth. So we can compare the solution, the optimal portfolio that comes from that sample covariance matrix, from the optimal portfolio that would be derived from the ground truth. The difference gives us the estimation error. So this approach allows us to estimate millions of errors that would come from applying this method, or the method that we want to evaluate on this given ground truth, where we can control for this ground truth, right? The process is known. We know the process, we have it under control. We can modify the process and see if the method is better or worse in a different example or a different setting. So once we have all of these different estimated errors, we can compute the root mean square error and see which method works better. This is what I've done here in this presentation. If you want to look at the code and understand exactly how the experiment is implemented, please look at the code snippets in my most recent book, Machine Learning for Asset Managers. It came out a month ago, and it was published by Cambridge University Press. You can download it from their website. What this experiment shows us is that when we optimize a portfolio without a shrinkage and without denoising, what we obtain is a very high error. The root mean square error is very high. Why? Because the covariance matrix is very unstable. The inverse covariance matrix has exploded because the covariance matrix, the original covariance matrix, is numerically ill-conditioned. how about we shrink the covariance matrix without denoising? Well, there is a small improvement. It's not a very high improvement, but yes, applying a shrinkage helps, and that's great news. Now, when we denoise the correlation matrix without a shrinkage, just denoising, no shrinkage, there is a substantial reduction in the root mean square error. The reduction is around 60%. Think about it. 60% reduction in the estimation error from simply fitting Marchenko-Pastor, separating the noise-related eigenvalues with the signal-related eigenvalues, and centering the noise-related eigenvalues. It's a relatively straightforward operation that helps us reduce the root mean square error in the estimation of the efficient frontier by 60%. And when we combine the two, denoise and shrinkage, essentially we get the same improvement as denoise alone. So what this tells us is that a shrinkage helps us a little bit, much less than denoising, and in fact, denoising accomplishes all the reduction that the shrinkage accomplishes. So there is a essentially perfect overlap between the two. It's just that denoising is more effective. We know intuitively what's the reason for that. The reason is that denoising accomplishes the same reduction in the variance of the inverse covariance matrix without losing information, without losing signal. The shrinkage loses signal. That's the price you pay for getting rid of the noise, while denoising gets rid of the noise while preserving all of the signal. So the result is intuitive. Not only it can be replicated through Monte Carlo experiments, but we know why it's better. How about when we compute the maximum Sharpe ratio portfolio? Well, when we compute the maximum Sharpe ratio portfolio, the results are even stronger. Why? Because if you remember from the second slide, computing the maximum Sharpe ratio portfolio requires multiplying the inverse covariance matrix with the vector of expected returns. And where vector of expected returns is quite inaccurate, we cannot forecast returns with any confidence. And when we multiply that vector of expected returns with an exploded covariance matrix, well, it's just garbage in, garbage out. However, when we denoise the correlation matrix, now there is a substantial improvement. In fact, we are able to reduce the root mean square error by 94%. Now, having worked in finance for over 20 years, it is rather unusual to find situations where a particular method can be so effective. A 94% reduction in root mean square error is very significant, and it tells us that this approach is very useful. It can be very helpful. We are not talking about a minor improvement. We are talking about a rather radical improvement in the stability of the efficient frontier. Let's go now to the second source of instability. First, I referred to noise-induced instability. Noise-induced instability, if you remember, is related to the number of observations. That's why in the Marchenko-Pastor equations, we found that the range of the eigenvalues was a function of T over N, right? You remember from the equations, if T over N is small, then the distribution widens. We need to have many observations for each variable that we utilize in our analysis. How about signal-induced instability? Where does it come from? How can signal be a source of instability? I think we all have on the back of our minds the notion that signal cannot be bad. How could signal make our work difficult? That's precisely what we are trying to monetize, what we are trying to utilize. Well, as it happens, signal can be a problem too. And this is something that the literature, I don't think, has studied enough. Typically, most researchers focus on noise-induced instability, and very few researchers pay attention to signal-induced instability. Let me motivate why signal-induced instability is actually very important. Consider the smallest system that you can think of, just two securities. The correlation matrix could have this form, right? Diagonals of ones, and then of diagonal elements of rho, the correlation matrix between the two securities. We can diagonalize this correlation matrix as CW equal W lambda, and where W, the matrix of eigenvectors, will have this form, and lambda, the matrix of eigenvalues, will have this form. As you can see, one of the eigenvalues will be 1 plus rho, and the other eigenvalue will be 1 minus rho. Now, as you know, the trace of the correlation matrix must be 2, right? The sum of the diagonal elements must be 2, 1 plus 1. But it also must be equal to the sum of the eigenvalues. So we know for sure that lambda 1 plus lambda 2 must be equal to 2. This means that when we have rho, when we have one eigenvalue that grows, it can only grow at the expense of the other eigenvalue becoming small, right? In fact, we can see that also when we compute the determinant of the correlation matrix. The determinant of the correlation matrix is going to be the product of the eigenvalues, and that's 1 plus rho times 1 minus rho, 1 minus rho squared. What this means is the following. We can only increase one eigenvalue at the expense of reducing the other eigenvalue, and that will cause that the correlation matrix will be smaller. The determinant of the correlation matrix will be smaller. This is problematic again because if the determinant becomes very small, now the inverse covariance matrix will explode and the entire solution will be very unstable. Now, why is this different from noise-induced instability? Well, because we reached this conclusion without ever mentioning T or N. You see, we reached this conclusion and we have never, we can reach this conclusion for any value T. So again, this source of instability is clearly different from noise-induced instability. It has nothing to do with T, the value, the number of observations. It has all to do with rho, the off-diagonal element. It has to do with the structure of the correlation matrix. We could use a correlation matrix computed on 10 billion observations. And if the rho is high, it means that 1 minus rho squared will make the determinant of the correlation matrix small. You see, it doesn't matter how many observations we utilize to estimate the correlation matrix. If the signal is such that rho, the off-diagonal elements are relatively high, then the solution will be extremely unstable. So what does this mean in the case of Markovitch? Well, why did we need Markovitch in the first place? We needed Markovitch's approach because we were dealing with a system of correlated securities. If the system was uncorrelated, if the securities were not correlated to each other, the optimal solution would be just an inverse variance allocation, right? We would just allocate money, assets, inversely proportional to the risk of the securities. And that would be an optimal solution if all of the off-diagonal elements are 0. So the reason we need Markovitch is because we expect rho to be significantly greater than 0. And that is precisely the reason where that is precisely the situation where Markovitch is supposed to fail. So let me state it clearly. The reason we need Markovitch is the same reason that will cause Markovitch to fail. So that's what I call Markovitch's course. Unless we address signal-induced instability, the very reason we need Markovitch will be the same reason that Markovitch will be defeated. How common is in finance to identify significant off-diagonal elements? Well, it's extremely common. When you think of sectors, regions, these shared, or I should say partially shared, these partially shared sources of risk mean that the financial correlation matrices tend to be clustered. They form clusters, where the clusters are either sectors, industries, countries, regions, etc. Companies that share the same suppliers, companies that share the same kind of investors or produce similar products, etc. The financial correlation metrics are highly clustered. And what does having clusters mean? Well, it means significant off-diagonal elements. And these off-diagonal elements cannot be detoned, right? Because they are not shared. These sources of risk, this mutual information is not shared by all of the securities. It's shared by some securities. For instance, the securities that belong to the same sector. So detoning is not even an option. What can we do? Well, we have to figure out a way to optimize this portfolio while controlling for signal-induced instability. And this is what we are going to see now, the NCO algorithm. NCO stands for Nested Cluster Optimization. The algorithm follows the following, these 5 steps. Step number 1 is correlation clustering. The first thing we need to do is we need to apply clustering algorithms, whether agglomerative or hierarchical, the algorithm of your choice. You can use the optimal number of cluster algorithms, the ONC algorithm, but you can apply other algorithms. The important is that now we are able to make a partition of our investment universe. The partition means that each security will belong to one and only one cluster. Given that, the second step is that we are going to optimize each cluster separately. If we have K clusters, we will optimize clusters 1 to K separately. This task can be parallelized, can be solved very quickly. And each of these optimizations will take much less time than optimizing the overall portfolio. Why? Because the system is much smaller. The step number 3 is system reduction. Now that we have estimated the optimal allocations for each cluster, we can reduce the system. Instead of working with an n by n system, where n is the number of securities, we can operate going forward with a k by k system, where k is the number of clusters. So in the fourth step, we compute the intercluster allocation. We compute how many assets should be allocated to each of the k clusters. Remember, in step 2, we computed the allocation intracluster. In step 4, we computed the allocation intercluster. What is the solution? The solution is computed in step 5. That's the dot product of the 2. We compute the dot product. Essentially, if we have allocated, let's say, 10% to one cluster, now this 10% will be sub-allocated using the weights estimated in step 2. Why does this method work? Well, Very intuitively, it works because we have taken an ill-posed problem and we have transformed it into a well-behaved problem. Why? Because once we have reduced the system from n by n to k by k, now we are guaranteed that the off-diagonal elements must be much smaller. Why are we guaranteed? Well, because that is the nature of clustering. The fact that all of these securities that belong to cluster 1 are bundled together is because they share the same sources of risk. Their mutual information was very high. And now that we are compressing, now that we are collapsing all of that information into a single loading, the correlation between this cluster and other clusters must be smaller. If the correlation was high, then these two clusters should have merged. The reason these two clusters did not merge means that their correlation must be low. Therefore, now the problem is well posed. Now Markovitch can truly succeed, now that we have addressed the signal-induced instability. By how much? How helpful is this approach? Well, we can repeat the same experiment that we applied earlier. We take a correlation matrix. In this case, I'm even taking a smaller correlation matrix. Before we experiment with a covariance matrix similar to the one associated with the S&P, 500 securities, 10 blocks, one block per sector. In this case, the results are such that even with a very small correlation matrix like 50 by 50, we will see a significant improvement. I won't go again through the description of the experiment. It's the same that we discussed before. The only difference is that now, instead of applying denoising, what we're going to do is we're going to apply the nested cluster optimization algorithm. Well, the results are that if we're using a minimum variance portfolio, the reduction in the root mean square error is around 47%. Again, very significant. Interestingly, applying a shrinkage is actually detrimental. Let me repeat this. When we shrink the correlation matrix and we try to apply a minimum variance optimization, in this case, the solution will actually be worse. And why is that? Well, because we know that a shrinkage is going to lose information. And when it loses information, as a result, even though we have control better for the noise, this loss of information leads to a worse solution. But what about combining both NCO and a shrinkage? Well, again, that's worse than just applying NCO. And the reason, again, is that a shrinkage loses signal, and that's precisely what NCO is trying to control for. So this goes to say that it is not even true that a shrinkage always helps, even if not much. In some cases, a shrinkage can actually be detrimental. How about computing the maximum Sharpe ratio portfolio? Essentially the same results. There is an improvement of 55% when you use NCO relative to applying Markovitch. Let me finalize with some thoughts about robustness analysis via Monte Carlo. I referred earlier that historical backtesting is not particularly effective or useful when we are trying to evaluate the mathematical properties of a particular algorithm. The information is that we are going to extract is essentially anecdotal. A better approach is Monte Carlo. Now, we can repeat this kind of procedure to evaluate multiple algorithms, not only Markovitch and NCO, but 20, 50 different algorithms. on a particular input. For instance, the input could be the Barra factor covariance matrix, and see what procedure is better for this particular input. So what I'm saying is that even though I like NCO very much as an algorithm, that doesn't mean that NCO will necessarily be the best option always. Depending on the kind of signal and noise that is contained in our input variables, there could be better algorithms to deal with these inputs. And how can we discover what algorithm is better for a particular problem? How can we identify what is the best tool for this job? And that's where Monte Carlo optimization selection helps. The steps are the following. First, we compute some input set, or we get the input set, for instance, from your favorite provider. And then we're going to produce a random draws that lead to sample inputs, sample new, sample B. Based on that, we can compute optimal allocations, and we can do that for 20, 50 different optimization algorithms, where we are going to evaluate, given these input variables, what is the solution that leads to the lowest root mean square error. So what I'm saying is that rather than expecting that there will be some algorithm that will dominate always, I would like that people are more experimental. They identify what is the particular tool for this set. And in that way, we don't need just to apply one method. We will have all of these algorithms in our toolbox, and we will apply the right tool for each job. Well, if you like this presentation and ideas that I discussed, I recommend you that you take a look at my two most recent books. One of them is this one, Advances in Financial Machine Learning, and also the newest one that came from Cambridge University Press, Machine Learning for Asset Managers, where you can find a lot of the code and a detailed explanation of what I have just discussed. And with that, Vincent, this is the time for questions. Thank you very much.
Awesome. Thank you very much, Marcos. So we've got a few questions from the audience. And before I quickly go to those, I'll just give people another chance to send over some last-minute questions if they have any once they've seen the presentation. But so the first one that was asked was, does the empirical matrix need to be column-centered?
The empirical covariance matrix needs to be the typical covariance matrix you compute. So you take a vector of expected returns. They can be relative to a benchmark or not, and you compute the covariance matrix. That's the only requirement. It will be a covariance matrix that is positive definite, but the approach is as general as that.
And next one, so from OMT, the estimate of the largest eigenvalue is based upwards. Should that be taken into account in the covariance and correlation metrics estimate? And if so, how? And how would this bias affect detoning and be incorporated into detoning?
Great question. So let me bring this slide, which is the relevant one. As you can see here, we compute the eigenvalues associated with the correlation matrix. And we know that theoretically, given Marchenko-Pastor, this is the highest eigenvalue that we expect from a random covariance matrix. And this is the smallest eigenvalue that we expect from a random covariance matrix. This is if the random covariance matrix is, if the covariance matrix is random. But of course, covariance matrices in finance are not random. They contain noise. They contain a lot of noise, but they also contain some signal. That's why we need to estimate. We need to fit the Marchenko-Pastor distribution, and that's what gives us this value lambda plus and this value lambda minus. So to answer directly the question, yes, there will be a maximum eigenvalue that we are estimating from our empirical correlation matrix, but that is not lambda plus. That is very likely the eigenvalue, the strongest eigenvalue, which is related to signal. What we need to compute is what is the highest eigenvalue associated with noise, and that's the one that we use to separate the two eigenvalues. And to fit this distribution, the Marchenko-Pastor distribution, we need to use machine learning, in particular kernel density estimation.
Great. And then I think a similar question, next one. What % of the number of eigenvalues is a good rule of thumb to denoise without denoising? Example, removing too much signal.
Great question. Well, I think that at least we are talking about one. When you think of the market component, that's the one that needs to be removed. Empirically, you can determine how many you need. Well, it will be, you can keep removing eigenvalues until you get a good clustering, until you get clustering with a very high p-value of the silhouette score. So experimentally, you can determine how many eigenvalues need to be detoned. How many? Well, how many? Whatever number you need to obtain a very high quality clustering.
Sure. Okay, bear with me with the next one. Now I'm going to do my best to try and read it out. Marchenko-Pastor PDF holds in the limiting case when NT is equal or more than inf for a fixed ratio. For the finite case, especially when the asset universe is small, 100 stocks, one can find the empirical equivalent MP spectral distribution that like a sharp cutoff point. Can it be more effective to denoise using a cutoff from the empirical finite MP PDF rather than the asymptote MP PDF?
That's a wonderful question. You're perfectly right. When we are talking about the very small covariance matrices like the one I used in the second example, that's why in particular I wanted to present an example with just 50 entries. In that case, Marchenko-Pastor may not be the most effective way. I still think that it will be much better than applying a shrinkage. We could test that, by the way, using Monte Carlo, but there are other approaches that you can use in that case. In fact, there is a paper that presents an heuristic. Maybe I can give you the actual. Yeah, there is a paper by Cockeret and Milo, 2014. We will put this paper in the with the slides that uses an heuristic to determine the cutoff point. I mean, a heuristic may be here the wrong term. It is essentially a rule of thumb, but that it is well informed, it's well motivated, it's not arbitrary, and that seems to be quite useful when we are dealing with small covariance matrices like 50 or nearly 100 variables.
Great. Couple more. So one additional problem with MO is that it produces non-sparse portfolios, effectively ignoring transition costs. Can NCO be adjusted to produce sparse portfolios, say with using ICA rather than PCA, that take into account the cost of acquiring a position?
Absolutely. And that is why I like that's why I like Monte Carlo approaches. You can simulate your experiment. You can design your experiment in the way you want it. It's under our control, and we can see whether adding now some transaction costs to this particular kind of covariance matrix helps. So your question is an excellent question because it glides really well towards what I said at the end of the presentation. Right? We need to be more experimental in finance. I think that we need to abandon this notion that there are some mathematical methods that will always be better, that will always dominate. We have to kind of abandon this sort of axiomatic mindset that we have in finance. We need to use math, of course, but we have to understand that finance is a very complex system, and we need to identify what is the best tool for each job.
And so on a similar note, have you experienced with different distributions heavier tailed for your simulations?
Yes. In fact, there are some very interesting contributions made by Gauthier Marty. He has applied GAN methods to produce complex covariance matrices. And again, please do not take this presentation as a claim that there will be a mathematical approach that will always dominate. I believe that's wrong. For each problem, you need to identify the right solution. NCO happens to be a very good approach for the kind of covariance matrices that we can utilize from Barra, for instance. But there will be some products, I don't know, maybe energy commodities, that will exhibit some traits that will require different tools, and that's where the Monte Carlo approach that I discussed at the end of the presentation comes helpful.
Perfect. And so final two questions in case anyone else wants to submit. We've still got a few minutes left. Penultimate one, what are the residue improvements of cluster size as a parameter versus RMSE in your final table?
Yes, so look, I like ONC. ONC is an approach that allows you to recover the number of clusters in a particular system. And again, Monte Carlo experiments show that it does so quite effectively. But depending on the size of the problem and also depending on the characteristics of the covariance matrix, you may want to use other approaches. I happen to like ONC a lot, but from time to time, I also use other methods, like, for instance, if I'm dealing with an extremely large covariance matrix and I need to compute a solution within minutes and I don't have the patience or the time or the computing power to apply ONC, which is quite computationally expensive, what I may do is to apply a hierarchical clustering algorithm where I control for the, I evaluate the t-value of the silhouette score and find a cutoff. You know, this is an operation that even with a 10,000 by 10,000 covariance matrix can be accomplished within minutes. ONC will take hours, and if you don't have hours, then you apply that approach, and guess what? It comes the answer quite approximate. It's a good approximation. So there are many different clustering methods in the literature that apply different linkage functions, and please be open-minded. You don't need to use what I have just discussed. In fact, I believe that the more methods you explore, the bigger will be your toolkit.
Perfect. And then final questions before we round up, then, more from a general sense, then, what would you say needs to happen for firms to modernize, and what are their current obstacles?
Yes, there are two kinds of obstacles. Number one is, like in many fields, in finance, there are generational biases and legacy methods. So Markovitch has been used for 60 years and will continue to be used, even though everybody recognizes all of the problems and limitations with Markovitch. This is just how the industry is set up. Now, over time, I believe that those legacy methods will disappear as people retire, and new methods will become prevalent. I think that what this tells you is that there is an opportunity here for those firms that embrace the new methods. They will have an edge, and even if that edge is not staggering, that's all you need in finance, right? In finance, a very small edge actually means the entire difference between success and failure. So I think that we are in a very interesting moment in finance because on one hand, we have more computing power than ever. We have better and bigger data sets than ever, which combined with machine learning gives us an edge. And the legacy methods are typically favored by very large asset managers, which means that there is a lot of alpha to be extracted. I would say that there is today more alpha to be monetized than ever before because the industry has consolidated into a very few extremely large asset managers that utilize legacy methods, and then many very small firms that are more dynamic, more effective, more modern. And as a result, there is an abundance of alpha that didn't exist before when the industry was much more uniform.
Well, what a fantastic way to finish off the presentation. Yeah, we've got no more questions. We've got one comment though saying kudos for a great presentation. And I'm sure the rest of our attendees could echo that as well. So yeah, thank you very much for your time, Marcos. And yeah, thank you to our audience as well for participating. So,
my absolute pleasure, and please stay safe.
Awesome. So thank you all for joining us today. If you did enjoy the webinar, please head over to QuantMinds LinkedIn page and let us know in the poll. And while you're there, you're more than welcome to stay connected with us. You can either follow us on LinkedIn or on Twitter at QuantMinds for all the latest updates on our face-to-face and online events, including webinars. Our next one will be tomorrow with Alexandre Antonov, and we hope you'll be able to join us once more. But for the meantime, thank you everyone. Stay safe and see you again soon.